Thanks, Subhath and Michael, for the kind introductions. As introduced, my name is Eric Ruggiero, and I'm coming to you all the way from sunny Cincinnati, and it's an absolute pleasure to be here with you, albeit virtually. I must admit, when I got up this morning, I really wish that this had been an invited seminar where I got to come down to Orlando, as I stepped outside to a balmy 22 degrees this morning, getting my children off to school. So believe me when I I'd much rather be there in person to deliver this message. So as introduced, I'm here today to talk to you a little bit about jet engines and the intersection with digital thread and what that means for us in the engine industry. By way of brief introduction, just so you're a little bit more aware of who I am, after graduation from Virginia Tech, I moved to upstate New York, joined GE's Research Center. Spent the first 9 years of my career at the Research Center before transitioning over to GE Aviation here in Cincinnati. Since I've been part of the aviation family, I've had the privilege of working on both the commercial side, servicing pretty much all of GE's flying commercial engines from a heat transfer, secondary flows, and durability standpoint. And most recently, I transitioned over and have been supporting our advanced military team, where I currently have responsibility for getting next generation platforms powered by some unique GE product offerings. And I guess I can just leave it at that. Before I jump into my talk today, I just wanted to mention, as I don't have any slide content that specifically addresses it, I just wanted to talk to you about history of GE's connection with UCF, as well as how to get in touch, and to highlight some of the collaborative efforts that are already ongoing. So in terms of the latter points regarding ongoing collaborations, I've had the distinct privilege of working with folks like Dr. Vasu, of course, who gave the introductory remarks today, and also with faculty members Jay Kapat and Kareem Ahmed, mostly in the areas of gas turbine heat transfer, as well as some novel combustion processes, and in particular, rotating detonation technologies, as well as some associated high fidelity sensors and diagnostics to accompany all three of those. And those collaborations have sprung up, at least that I've been personally involved. It comes from the connections at events like this, or at bumping into each other at events like AIAA and ASME conferences. So I hope that is one opportunity that we can all be afforded sometime here in the near future as the world opens back up post-COVID-19. In the interim, I'm more than happy to share my email address, and if anyone has any questions or comments or thoughts around potential collaborative opportunities, I'd love to make myself available to you for us to discuss that moving forward. So with that as a backdrop, let's jump into today's topic, which is around how to go about spinning digital threads in aerospace. So I like to start off with this time animated or time-lapsed video that is circa around 2010 and was released by Zurich's School of Applied Sciences. So what you see here is in this time-lapse video is every yellow dot on this screen represents an actual aircraft in flight at a given snapshot in time. And, being an aviation and a gas turbine enthusiast, this absolutely jazzes me up. And although the skies don't look like this currently, I'm very much looking forward to them looking like this again in the not too distant future, once we get vaccinations rolled out across the globe. And I really get motivated by this, not just because I love aircraft and in particular aircraft engines. I get motivated by this for two reasons. First, I love the fact that I get to work on technology that helps to bring together people from across the globe, not just family and friends, but also business partners and collaborations where new ideas and innovation comes from. The other part of getting to work in this aviation sector that's been really exciting for me is, especially from my days working on the commercial market where GE's got a tremendous footprint of engines that are flying around, is that, for every 0.1% of improvement on a given gas turbine engine that, working with my team and working across the aviation enterprise that we can bring to bear for a given customer, that immediately gets a magnification at this global scale, and really helps in terms of things like the reduction of carbon footprint, extension of time on wing for from a durability standpoint, and just at the end of the day, saving on gas costs, Jet A costs, fuel costs for a given operator. And that's really been, part of the reason why I moved to the aviation business from the research sector. But it's something that really helps me to jump out of bed every morning to know that I'm helping to contribute through my team to this kind of global mindset. So then I want to bring this back into focus for today's talk. Another unique thing that's happened in the last few years here, as we've just increased computational capability, storage devices, connectivity, and the like, I no longer look at just the physical side of what it takes to make and to build and to fly safely a jet engine. I now look at a chart like this video is showing, and I see an opportunity where each of these dots represents a potential data stream to us. And what can I do with that data in order to unlock new capability and new value for each of the operators that we're blessed to engage with? So with that kind of framework in mind, my talk today is going to cover 3 points. First, I want to spend a little bit of time talking about the Amazon business model and why I feel that that's a great analogy to what we've been working here at GE Aviation on the digital front as it comes to our engines. Then I'm going to transition that to highlight for you some of the key salient features of what it takes to work within that data framework to unlock that value for our customers. And then in my closing remarks, I hope to leave you with some good questions to start to get you thinking about the world a little bit differently, about your research a little bit differently, to help us to figure out what's next and on the horizon. So first off, let's talk about what we can learn from Amazon. So if you're like me, you probably have an Amazon Prime account. And if you ever look up on Amazon's website, you may or may not know, but they actually pride themselves with their mission statement being that they want to be Earth's most customer-centric company. And as an Amazon Prime member, I absolutely feel like Amazon is living up to their mission statement, especially with the number of packages that seem to show up on my door, sometimes knowingly and sometimes unknowingly, depending on what my wife's interests are on any particular day. But anyway, so what I wanted to point out here, so I found this schematic from the business school at Syracuse University. And what I like is that in just kind of a single snapshot, it highlights something that I think is really critical here to how Amazon goes about living up to this mission statement. If you notice, Amazon's Amazon's business model starts and ends with you and with me, actually on an individual basis for every account that they have out there. And they all of the logistics that happen in between, from when I have the idea that I need to purchase something all the way through to getting it to my doorstep. Now that kind of convenience comes at a price. The price that I pay for that is my willingness to share key pieces of data with Amazon around the customizations and the preferences of the types of products that I am interested in, that I want delivered to my doorstep. But I'm willing to pay that price and to freely offer up that data because I love the fact that they are doing everything in between and making sure that they're going about delighting me at the end of the day. So probably, in this day and age, it's probably not a huge surprise to you, but Amazon is building up digital twins of you and of me for each of our accounts based on the preferences that we share. So in this model here, here's my digital twin that show up, and I really appreciate the flattery of Amazon sharing this image of me, of the model that they have built up on their end. But in any case, so what they're doing is every time that I'm making a click, every time I'm browsing through and perusing their website and making choices and figuring and even seeing like which part of the market space from a price standpoint that I am most interested in, they are taking all of that data and creating that digital twin model of me so that they can go out and they can run their own sophisticated algorithms to help to predict what they think I'm going to like next. And sometimes, that this shows up in the top of the screen as a new deal of the day, that of an item that I didn't even know I wanted, but as soon as I see it, sometimes I go, hey, you know what? I really want that. And so this is what I'm trying to highlight through this business model here is, again, my free exchange of data allows Amazon to build up these models that allow them to bring to bear to my attention what products and that they think that I'm going to like. And at the end of the day, I do end up liking, and helps to really expedite that process. So they're capitalizing on that, but at the same time, I love it because they truly are delighting me as the customer. So now what I want to do is I want to take this kind of mindset and I want to transition it over to us at GE Aviation. I really want to be able to do the same sort of thing, but now instead of with little brown boxes, I want to do this with, at a jet engine scale. And an OEM like GE Aviation is uniquely situated to learn an awful lot and to know an awful lot about the products that we put out there. So if you think about a gas turbine engine on the commercial side that's hanging from a given aircraft, as an OEM, I get keen insights at the part level for some of the key characteristics of that part as it's being produced in supply chain. I then get additional data as that part is put into a kit at the module level that makes that module unique. That module then gets strung together with other modules to build up the actual overall engine. And again, I can create a meta model that captures those unique details. And then I provide that to you you as a customer, as an operator, to hang that engine on an aircraft. And then at that point, there's another level of data stream that comes in. Where are you flying that aircraft? What airport pairs are you taking that aircraft and subjecting, the engines that are hanging from that aircraft to? How are your pilots flying that aircraft? And, what sort of, from like a durability or life cycle standpoint, how are they taxing the engine in how they're flying that air vehicle? And then lastly, there's other, considerations that can come into play as well in terms of not just airport pairs, but what are ambient conditions that are present? What is the environment like? All these layers of data can then be brought together in one data link to help to build out new insights, keen insights as to what's going on for the products that you've purchased and are operating. Say as an airline operator. And so therefore, GE Aviation is well positioned to be able to talk to you about things like the current health state of your engine and of the various parts that make up the modules. We can help with things like fleet optimization, how you go about using not just a single aircraft, but rather the fleet of aircraft at your disposal to optimize things like performance versus durability. And at the end of the day, the idea is to help to bring home even more improved reliability, both at the engine and overall aircraft operation level. And all of these value streams really at the end of the day are brought together because of looking at this through the lens of the digital thread. So let me give you an example of some of the data sets that we collect routinely as it relates specifically to an in-flight and two different types of classes of data that we're collecting. On the left-hand side here, the first type of data we collect is what we call snapshot data. It's typically 3 unique moments in a given flight envelope. Typically it's takeoff, climb, and cruise, where we actually sample at a fairly high frequency, so tens of hertz up to hundreds of hertz, key parameters of what's going on, again, at these critical points in the flight envelope. And then this data tends to be available to us in fairly real time through the ACARS system for data transmission. On the right-hand side here, you'll see an example of the other type of data that we're collecting for every single flight. So this is called continuous engine operational data. This is typically recorded at about a hertz. And again, this is now over the entire flight envelope, from taxi all the way through landing and taxi again. And so to kind of put things in perspective to you, as you can imagine, think about all those dots that were flying around in that video series I showed you in my introduction. This generates a tremendous amount of data on a day-to-day basis. So just to give you a ballpark, for our GEnx engine, which is what powers, for example, the Boeing 787 Dreamliner, we tend to collect about 5,000 data points every second of that flight. And anytime a 787 lands, we're looking at on the order of about a ½ terabyte of data that's available to us. Now, where I mentioned the snapshot data gets transmitted, on the other hand, on the right-hand side, this continuous engine operational data, this is not transmitted. This is something that needs to be manually downloaded at the end of a flight segment or a series of flight segments. Okay, so I've all this data that I'm collecting. So what am I going to do with it? Just like that Amazon model that I shared with you earlier, of course, now we want to go about building up digital twins again, at the component level, at the module level, or at the engine level, to help to monitor what's going on for that particular engine, given all the other parameters of how that engine's being operated by a given flight crew, to where it's being operated across the globe from airport pair to airport pair. And so we can build up with pretty high fidelity this digital twin model of that asset. And what we can do is we can start to run our own machine learning and AI type algorithms in the background to truly exercise and to forecast out based on current usage. How are you doing with respect to the overall, say, both performance as well as durability of that particular asset. And so, again, in much as the same way as that analogy as the Amazon business model, in exchange for that data that the operator is sharing with us, our goal is to unlock this value, help to ensure that the operator is optimally operating both the engine itself, on that aircraft, and then also how they're operating their fleet to maximize on things like product durability as well as performance. At the end of the day, nobody likes surprises, and this type of mindset and methodology is a way for us to work with our operators to help to minimize the amount of surprises that occur. So recognizing that some of you on the call might not be all that familiar with the gas turbine ecosystem, I just wanted to spend just a few more minutes here to highlight for you some of the key attributes of a given turbine ecosystem, and then to drive home this point of how analytics-based maintenance, how that plays into the value stream for our customers. So I'm showing here, kind of a cutaway cartoon of one of our narrow body products. This is the LEAP engine that flies on, say, a Boeing 737 or Airbus A320neo. So if you're not all that familiar with a gas turbine, I'm going to walk you from front to back just briefly, just to highlight some of the key features when I talk about the modules that make up an engine. So first, on the front end, as you enter the nacelle, you encounter the fan. Fan's responsible for pumping most of the flow, of course, through and around the engine, which is why we call these high bypass ratio turbofan engines. So that fan pumps flow around the engine, but also pumps flow into the core. That air that enters into the core of the engine first needs to get squeezed down and brought to a very high pressure, and that's done through the high pressure compressor. The flow that comes out of the high pressure air that is coming out of the compressor then dumps into the combustor chamber. From there, through the ignition of Jet A, we then bump up the temperature. So you have high pressure, high temperature air that's available to you. And immediately downstream of that, you then enter into the turbine module. In this case here, the HPT, or high pressure turbine. HPT is there to extract useful work from that high pressure, high temperature fluid in order to drive the HPC, the compressor. Further, that flow is expanded out, then passes through the low pressure turbine, which is what's driving your fan in this direct drive type, which is GE's preferred consideration for engines like this. And then the balance of flow comes out as accelerated out through the back of the engine, and that's where we're creating useful thrust for the aircraft. Now, from my days on the commercial side of the business here at Aviation, I spend a lot of time looking at the combustor as well as the high pressure turbine. So I'd like to take just a little bit deeper dive and show you a cross section of what typical HPT and combustor looks like. And that's shown here. Now I am switching engine variants on you. So this is the cross section of GE 90-115B, which is one of our larger engines and flies on the Boeing 777. This is the precursor, for those of you who are aviation enthusiasts, this is the precursor engine to the recently certified GE 9X engine, which is going to fly on the Boeing 777X in the not too distant future. So back to the schematic that you can see here on the screen. So on the left-hand side, so flow is going from left to right in this cross section. And on the left-hand side, I've got very high pressure air that's dumping out from that compressor through the diffuser. That high pressure air then spills around the combustion zone, which is represented by these liners here, where I've got these fuel nozzles shown on the left-hand side, left-hand, say, dead center side of the image. Got fuel nozzles that are going through the combustion process with Jet A in order to, again, raise that temperature of that high pressure air. That high pressure, high temperature air is then dumped downstream and accelerated through the turbine nozzle, and then encounters the first set of rotating turbine airfoils, which we call turbine blades. Now these blades run at very high speed and need to run at a very tight radial clearance to these other components that are stationary just north of the tips of these blades, and we call those in the GE Aviation vernacular shrouds or tip shrouds. These shrouds, their job and their function is to ensure that all of that very precious, high value, high temperature, high pressure flow does not leak past and escape past this high pressure turbine blade, because that's essentially losses that are introduced into the system, and my engine is not going to operate at the same level of performance, as I open up these gaps. And so our ability to track the existing state of the health of these shrouds is critical to helping to ensure that the jet engine is operating where we need it to for our customers from a performance standpoint. So with that in mind, we developed some of our, early on, we developed some cumulative damage models, or CEM, to capture the behavior, the progression of damage within these high pressure turbine shrouds. And you'll notice from the chart that's shown here on the screen, I've got cycles on the x-axis and then this accumulated distress on the y-axis. You'll notice that there are two distinct curves or lines that show up on this chart. These curves correlate to different airport pairs, and the lesser of these two curves, the less steep curve, correlates to less tax on how that particular engine is being operated compared to this more steep curve. So because of the CEM and because of its introduction, we can now provide this kind of insight to a given operator. And, we were able to work with operators to say, hey, you're currently on a trajectory that's going to truly accelerate the degradation of these shrouds, which then translates to degraded performance of the engine. So you might want to consider, either changing how the engine's being operated, or perhaps consider cycling which airport pairs you're using those engines to service. And in doing so, we're able to proactively manage and help the operators shift from this more extreme line down to this other curve. So this is just an illustrative example of the kind of value that we're trying to bring to bear for our customers. So getting toward the conclusion of my talk, As you look to the future and some of the upcoming research areas that might be of interest to this community at UCF, I just want to quickly touch on a few questions that I'm always curious to hear your thoughts and otherwise. Starting at the top here, as I mentioned, we're filling up the data lake with a tremendous amount of data sets on a daily basis. So what are the most efficient, optimal ways that we can start to go about visualizing these data sets to extract the most amount of knowledge and value and insight for our operators? Continuing around here, with the advent of additive technology, now I've got a means of manufacturing at my disposal that is light years faster than some traditional means of manufacturing. Is there something that I can learn early on in an engine program and translate the data that I'm collecting from the field to help to bring about new part design, whether it's for that fleet or for a new engine build or whatever the case might be? But I think that that's really an intriguing direction and that research can take. Really want to, especially when you consider the operational data and how customers and operators are using the aircraft and these engines, how can we get even smarter at tailoring our service programs to help to ensure that we're meeting the needs in a timely manner to really help to bring the most amount of value to the customer? Because the more time on wing that you have in between shop visits is more value that's unlocked for a given customer segment. You can also think about other apps that can be built, with all this data that we're extracting, that we can, help pilots and crews, or an even more salient example is a lot of aircraft sadly have been parked because of the last year's worth of, pandemic. How do you go about using the existing data on each of those engines that are hanging on those parked aircraft to help the customer make informed decisions on which aircraft to fly and when, as they're coming back into service? And then lastly, instrumentation is always at a premium for a given engine. So in the absence of being able to put more instrumentation on, especially for an existing certified engine, what are some ways that I can get creative on essentially creating a virtual instrumentation suite to extract even more insights and to help to understand better the state of health for a given asset? Coming back to that image that I opened up with, this is part of the why I'm excited about working in the aerospace industry, and in particular on jet engines. I hope through my discourse today, I've given you something to think about. And for those of you who weren't already thinking about it, I hope you'll challenge yourselves to see each of these, aircraft engines that are, hanging from a given aircraft, not just for the beautiful piece of engineering marvel that they are, but also as a tremendous source and wealth of new field of engineering data to help us on the road ahead. And in closing comments here, my last chart, so what I want to leave you with is this. So first and foremost, the digital industrial revolution is absolutely here, and it's going to be part of our future, not just for jet engines, but across multiple industries. For those of you who are teaching faculty and teaching researchers and directly engaged with students, I cannot stress enough the importance of your ability to highlight and to train students to embrace the fundamentals on the physics and the engineering and the core courses that they're taking. And then at the same time, to use that fundamental knowledge and to think about how do I bring in the digital data stream with that to, again, get those unique insights. Hopefully you can challenge yourself to think in this kind of framework, for your own research, and to think about what exciting collaborative opportunities may come next. And last but not least, I hope that you'll keep in mind this analogy I brought to bear around, the Amazon business model and how it applies to aviation and in particular jet engines. I really think that this is, the way of the future. And it's really exciting to think about the potential that's going to be unlocked through digital twin and digital thread technology. So thank you very much again for the opportunity to share these thoughts with you. And like was said, I'm going to stick around and would love to answer any questions that might be on your mind. Thank you again.